crash course. And now we are down to our 7th crash course on properties of simple mixtures. For today, we'll be discussing first the chemical potential, thermodynamics of mixing, colligative properties of solutions, and activity of ion solution. Okay. So here, guys, we have to describe the properties of simple mixtures because in simple mixtures we have open systems. Okay. They were earlier at thermodynamics we studied a lot of closed systems. Now we will study open systems with varying composition. Okay. So with that, open systems, guys, they require partial molar quantities in order to describe the thermodynamic behavior of various phases in an open system. Okay. So we will use the chemical potential, okay, which represents a change in Gibbs energy with respect to composition, to determine the thermodynamics of mixing for simple mixtures and the colligative properties of solutions. Okay, so I hope that Gina, guys, we will see it. So what is a partial molar quantity? So a partial molar quantity tells us how much of a property, such as energy or volume, will change when we add just a tiny bit of a substance. Okay, for example, substance J, while we keep everything else, when we keep other variables the same. Okay, it's like para kayo nagtatanong, guys, pag dinagdagan ko ba ng isang spoon ng sugar ang tea ko, gaano kayang natatamis? How much sweeter will it get? Okay, that sweetness change per spoon, para siyang partial molar quantity. Okay, it's about how much a specific component will contribute to the overall mixture. Okay, so ang isang partial molar quantity, it will always ask you, if magdadagdag ako ng this one thing, okay, paano mag-change ang buong system na yun? Paano mag-change ang property ng buong system na yun? So, just like we add sugar to increase sweetness, okay, adding a chemical substance, gaya ng gas, ion, or molecule, it changes the energy of a system. For example, nag-experiment system ka, tapos nagdagdag ka ng chemical substance, nagdagdag ka ng ion, molecule, or gas, okay? So that changes its energy. Now, that change in energy per mole of that substance is what we call the chemical potential. Okay, so energy per mole of that substance, okay, that is the chemical potential. So we can define chemical potential as mu J. So this mu J, okay, it is the amount by which a system's energy changes when you add a tiny amount of substance J. So we describe how a system's energy will change, okay, as we add J substance, okay, while keeping temperature, pressure, and other variables constant, okay. So guys, nagdadagdag tayo ng amount of a component, okay. So compositions naman tayo ngayon while keeping temperature and pressure constant. So let's formally define the chemical potential again. Chemical potential mu represents the partial molar quantity for Gibbs free energy. And isa siyang intensive property. Okay? Okay, so it just describes the tendency of a substance to change. Yan, so yun yung keyword, guys. Tendency of a substance to change. Mina-measure niya. As we add 1 mole of a substance to a large amount of mixture at constant TNP. So guys, ang requirement is magdadagdag ka ng maliit na amount of the substance, 1 mole of a substance to a large amount of mixture given that temperature and pressure are constant. So how do we get the chemical potential? Okay? The chemical potential is equal to G1 bar. It is equal to the partial derivative G divided by the partial derivative of the number of moles for constituent 1, okay? Given that temperature, pressure, and the number of moles of constituent 2 or substance 2, number of moles of substance 3 to substance J are constant. Okay, so again, mu1, we will find the chemical potential of substance 1 or its tendency to change, okay? And then G, this is the Gibbs free energy of the whole system, okay? But this time we have here G1. Pag sinabi natin G1, guys, okay, we are just considering the Gibbs free energy of what? Of constituent 1, of substance 1, of component 1 in the whole system. So kung marami kayong components. So kinakonsider natin sa G1, guys, yung Gibbs free energy lang ng substance 1, component 1, okay? And 1, again, the number of moles of substance 1, okay? And how much, specifically how much of it in the system, okay? Now, the partial derivative here, okay? This means how much G will change when we add a tiny more of substance 1, okay? Tiny more of substance 1, okay? So, basically, guys, the chemical potential of substance 1 is a change in the system's Gibbs free energy when you add a tiny bit more of substance 1, okay? While we keep temperature, pressure, and the other substances, other amount of the substances constant, okay? That's clear, guys? So, with that, we can define that the total Gibbs free energy for a binary mixture. So, pag natin binary mixture, guys, meron tayong two components. Meron tayong component A and component B. So, the total Gibbs free energy for a binary mixture can be determined from the fundamental equation, guys. If you recall, we have discussed the fundamental equation for G. So, we can find the dG, okay, for a binary mixture. And that is, dG is equal to negative SVP plus VDP plus mu A dNA plus mu B dNB. So, dito tinatake account na natin, guys, ang chemical potential ng component A and component B sa binary mixture nyo. Okay? So, this equation will tell you how the Gibbs free energy of a system will change when temperature changes, pressure changes, and the amount of substances A and B will change. Okay? So guys, again, chemical potential tendency of a substance to change. So, recall that equilibrium will be achieved if delta G is equal to 0. Thus, what can we say if a binary mixture has phases A and B in equilibrium? Ano masasabi natin, guys? Ang Gibbs free energy ng phase A, okay, or substance A, is just equal to the Gibbs free energy for B. Okay? Kasi in equilibrium sila. Again, we can achieve equilibrium if delta G is equal to 0. So, GB minus GA must be equal to 0. Okay? So, how can we relate this to the chemical potential of phases A and B in equilibrium? In equilibrium, guys, tandaan, partial molar quantities naman ng chemical potential, and you have to see here the tendency of the substance change. Okay? So, it will be the chemical potential of phase A is equal to the chemical potential of phase B. Okay? I hope it's clear, guys. So, sinasabi lang dito, at equilibrium, yung chemical potential ng species must be the same for all phases in the system. So, let's say meron kang phase A and phase B, okay? Ang chemical potential ng species na yan, okay, must be the same for all phases in the system. Okay? Kasi equilibrium sila eh. Di ba? Nag-exchange lang yan. Nag-exchange tayo between phase A and phase B. Okay? So, guys, how can we see this? How can we visualize this? Tingnan nito. So, for a T mixture, ang pwede yan, ang halintulad ng yan ay ang isang chemical system. So, we can look at the chemical system as a T mixture. Okay? And then, yung mole ng isang chemical substance, say NJ, okay? It is represented by a spoon of sugar. Okay? Now, titingnan natin dito, guys, yung what? Energy, effects sa ating energy. So, that can be U, H, A, etc. So, U gives general energy, H, enthalpy, A, Helmholtz free energy, etc. So, pwede natin siyang halintulad, guys, sa sweet test naman ng inyong T mixture. Now, the chemical potential change in energy per mole, which is equal to mu J, to, pwede din natin siyang ihalin tulad sa change in sweetness per spoon. Okay? Dapat clear yan, guys. Again, ha? Hinahanap natin ang tendency of a substance change, the change in energy per mole for the chemical potential. Okay? Now, guys, other extensive properties, kagaya ng internal energy, enthalpy, and Helmholtz free energy, okay, we can actually determine their respective chemical potentials. Okay? So, for example, dito sa first row, this represents the partial molar quantity equation for the internal energy. Okay, sinasabi lang dito, guys, the change in internal energy, U, kapag nagdagdag tayo ng tiny amount of component J while keeping entropy, volume, and all other components fixed. Okay? Ganon ang meaning. Okay? Next we have, so for example, guys, anong sinasabi niya? Pag nagdadagdag ka ng more of substance J sa system mo, okay, ang mu J mo, the chemical potential, it will measure how does the energy stored inside the internal energy change. Okay? And again, it is dependent on entropy or how spread out the energy will be. It is dependent on volume and what's already in the mix, so in the composition. Okay? Next. Okay? Here, guys, we have a partial molar quantity for enthalpy. Okay? Sinasabi lang dito, the change in enthalpy H, okay, which we know is the energy plus pressure volume work, diba? Okay? When we add a tiny amount of substance J. Okay? And here, we will keep entropy, pressure, and the other components constant. So sinasabi lang dito, guys, how much heat content or how much useful energy, diba? Yun yung definition of enthalpy, how much of it will change when you add more of substance J. Yun yung denominator nyo. Okay? And again, that depends on entropy, pressure, and other substances in the system. Lastly, this is a partial molar quantity equation for Helmholtz free energy. And sinasabi lang dito sa equation na to, the change in Helmholtz free energy A. Okay? So A, guys, Helmholtz free energy, it is the useful energy, diba? Useful energy at constant volume and temperature upon adding more of substance J while keeping temperature, volume, and others such as composition constant. So sinasabi lang ng equation nito, guys, okay? Sinasabi lang ng chemical potential ng substance J for a Helmholtz free energy, how much useful work ang makukuha mo from the system if you add more of substance J. And again, it is dependent on temperature, volume, and what's already mixed in, yung composition. Okay? I hope it's clear, guys. Ganun mag-analyze, okay? So let's proceed. Ayan. Now, another concept here, based on these equations, is based on the Gibbs-Duhem equation. Okay? So sinasabi lang dito, guys, okay? Pag nag-increase ka slightly, if you slightly increase the chemical potential of A, okay? If you slightly increase the chemical potential of A, ito, then the chemical potential of B, dapat mag-decrease yan to compensate. Okay? Again, dapat mag-decrease ang chemical potential ni B if mag-increase ang chemical potential ni A. Okay? Kasi guys, yung chemical potentials ng components ng isang system, let's say yung components yung A and B, okay? Guys, hindi sila independent from each other. Diba? Kasi there are two components of one system. They are in one system. Therefore, if the chemical potential of one component, kagaya ng component A, it will change, then dapat yung chemical potential ni B mag-adjust din to keep the system balance. Okay? To keep the equilibrium. Okay? So, anong yung sinasabi, guys, naman ng ratio na ito? Negative NA over N over B. NB, sorry. So, the ratio of NA over NB just tells you how much it will change. How much it will change based on how much of each substance is present. Okay? Yes, guys. Okay. Now, let's proceed to the factors affecting the chemical potential. Okay. So, tandaan nyo lang, guys, ang mga systems, any systems, they will naturally move toward lower energy states. Again, lower energy states. Okay. Therefore, higher chemical potential means a substance kailangan niya ng energetic potential. Kailangan niya ng energy, okay, to react and form products with lower chemical potential. Again, yung mga gusto ng high potential, gusto nila, okay, may enough energy to react and form products with lower chemical potential. Now, since, guys, chemical potential, it is dependent on temperature and pressure, now we will see changes in these conditions that will shift the stability and reactivity of the substance. So here, guys, look at this figure here. Now, when you increase the temperature, okay, let's increase the temperature, that's x-axis, okay, the molecules, diba, they will move faster and they will move more freely, okay? Ano mangyayari, guys? Exactly. Yung system natin, since they move faster, they move freely, our system becomes more disordered, magulo. Therefore, the entropy will increase. Okay? Now, since the molecules, diba, kunwari, nasa container sila, okay, dito na yan, since sa container sila, tapos they will move more freely, okay, mas spread out ang molecules mo, okay, as you increase the temperature. Ano nangyayari pag spread out ang molecules? Edi, less eager sila to do work or react. Gusto nila magkakalayo sila from each other. Ayaw nila mag-do ng work or react. That's why, what will happen to the chemical potential? Okay? Again, chemical potential, guys, it describes their energy to drive change, diba? Yung energy ng system to drive change. Hey guys, spread out na yung molecules, diba? Ayaw nilang mag-work or mag-react together ng mga molecules na yan. So, yung chemical potential which is like their energy to drive change, okay, it will decrease. Okay? So, let's describe that for solid, liquid, and gas. So for solid here, tingnan nyo, guys, yung decrease in the chemical potential, very small lang, diba? Ang decrease packet. So for solids, diba, we know that molecules, they vibrate a bit more, diba? However, they are still tightly packed. So kapag nag-increase ng temperature, okay, in a solid, then yung mga molecules yung mag-vibrate yan, pero tightly packed yan sila, diba? So what will happen? Entropy will only increase slightly, okay? Kasi may onting motion tayo. Now, what will happen to the chemical potential? It will drop lang in small differences. Tingnan nyo, guys, diba? Nag-decrease lang siya very, very slightly. Okay? O bakit nangyayari yan? Kasi, guys, diba, we know that solids, they are already ordered. They have an ordered structure. Okay? So they do not need much change. Okay? They do not need much change. Therefore, we only have a small decrease in mu, or the chemical potential. Tandaan, guys, ha, mu, it is a tendency of a substance change. Next naman, let's look at the liquids. Here, this time, we have a steeper line. Okay? Steeper curve. Okay? As we increase the temperature, mas nagdi-decrease ang ating chemical potential in liquids compared to solids. Bakit? So, unlike solids, diba, liquids, the molecules, they will move around more freely. Diba? Kasi, what? Further apart, diba, molecules in liquids, now what will happen to entropy? So, entropy, it will increase more. Therefore, there is more randomness in your system. Okay? So, ano mangyayari sa chemical potential? Okay? The chemical potential, it will drop more than in solids. Okay? The chemical potential, it will drop more than in solids. Okay? So, there will be a moderate decrease in the chemical potential. And lastly, for gases, we have the steepest curve here. Okay? And we know that in gases, guys, compared to liquid and solids, they are their molecules are more far apart. So their molecules, they move very, very fast because they are far apart and they spread out a lot. Now, this results in a huge increase in entropy and therefore very high disorder. Okay? So mangyayari sa chemical potential, guys, the chemical potential, it will drop by a lot. Okay? Magdidikit siya ng sobra. Bakit? Kasi diba, guys, in a gas, yung mga gas molecules nyo kasi, okay, they are super free. Okay? They are super free. So, ano mangyayari? Ayaw nila mag-react together. O, ayaw nila mag-come together and mag-react. Okay? So, there is not much change for the chemical potential. Okay? Wala silang drive, wala silang tendency to change. Kasi the molecules, they are just very, very, very far apart. Okay? They are less eager to do some work or react together kasi magkakalayo ang mga molecules na yan sa isa't isa. Therefore, the chemical potential will decrease much more compared to liquids and solids. Okay? I hope that's clear, guys. So again, for gases, we have a large decrease in the chemical potential. So, in summary, guys, ayan yan. Okay? I hope that's clear. So, dito, compare lang natin ang decrease ng chemical potential with temperature for a solid, liquid, and gas. Now, guys, let's go back to this dito. Okay? Sabi dito, guys, okay, when temperature increases, then chemical potential decreases. Again, that's because the molecules, they are more further apart when you increase the temperature, right? Kaya, they have a very low tendency to change. Kasi gusto nila malayo sila sa isa't isa. Okay? Wala silang tendency to change kasi they are far apart, so they will not react together. Okay? They will not react together. Okay? That's why chemical potential decreases. And what can we say about the slope? So the slope of this, the slope of the line for this is represented by the change in the chemical potential, okay, given the change in temperature. Tama naman, di ba? Okay. And this is given by the negative of entropy. Tama naman, di ba? Negative ang ating slope dito. Negative entropy. Okay? So, if this has a great change, guys, syempre, mas nagiging negative ang ating slope. Yan, di ba? If this increases, if the S increases, entropy increases, di ba? Especially for gas, ang nangyayari sa slope ng inyong curve dito, it increases. Kaya, mas steep ang gas. Okay? I hope it's clear, guys. Let's proceed. Let's proceed with pressure naman. Okay. So, for pressure, okay, sinasabi lang dito, guys, as pressure increases, molecules, they will pack more tightly, di ba? Di ba yun yung concept natin? Imagine nyo, guys, in-increase yung pressure, syempre yung molecules, they will pack more tightly. What happens? So yung molecules, they will interact more with each other kasi they are packed more tightly. And that raises the system's energy and it makes it harder for them to add more particles. Okay? And this leads to an increase in the chemical potential. Bakit? Okay? So guys, imagine nyo lang, yung molecules, get squeezed closer together. Okay? There is less space between them and more interaction between them. Okay? So adding more particles becomes harder. You would need more energy. You would need more energy to drive the substance. Okay? You will have to have more energy to drive the substance. Okay? In order to change it. Okay? Again, you have to add in more energy. Okay? In order to add in more particles. So, dyan guys, nag-increase ang ating chemical potential. Because we increase the amount of energy we need in order to drive change. Again, we need more energy. We need more amount of energy in order to drive the change. Okay? In the system. Okay? So, guys, isipin nyo yung chemical potential. Okay? Para siyang cost. Para siyang effort. Diba? To add one more particle to the system. Okay? So, bakit nag-increase nga ang chemical potential as the pressure goes up? Kasi guys, kapag maliit lang pressure, low ang pressure, the particles, they have plenty of space. Diba? They have plenty of space kasi you have low pressure. So, anong meaning yan? It is easy and cheap to add another particle sa ating system. Again, it is easy and cheap to add another particle. Okay? So, we only need a lower chemical potential. Okay? We only need a small amount of energy in order to drive the change, in order to add one more particle. However, when we increase the pressure, okay, again, the particles pack tightly sila. Okay? Nagpupush sila against each other. So, when you add one more particle na pabida, di ba? That means you are pushing the particles much even closer. And that takes more energy kasi pinupush mo sila lalo to interact with each other. Again, that takes up more energy. Okay? Parang, kunwari guys, late ka na sa pasok mo, late ka na sa school, late ka na sa work, di ba? Tapos puno na yung elevator, tapos pinilit mo yung sarili mo na kumasya. Ganun yun, okay? That requires a lot of energy, okay? To add in one more particle, to add in one more person, di ba? Sobrang effort pa guys, makipagsikipan pa tayo, di ba? Ano mangyayari sa ibang molecules or sa ibang tao? Hindi sila din, di ba? They have to, use up their energy para mag-interact with other molecules, di ba? Ganon, okay? That's why we have a higher chemical potential as pressure increases, okay? So, in this graph, guys, okay, as we increase the pressure, okay, for a gas, here, we have a large increase in the chemical potential. Di ba? O bakit? Diba guys, there is a large difference kasi for a gas. So example, if you increase the pressure for a gas, edi, yung gas, diba, nung una, they are very spaced out, diba? Freely moving sila. Pero kung in-increase mo yung pressure na yan, napipilitan mo silang, mag-interact with each other. Eh, diba, sa gases, dapat far apart nga sila as much as possible with each other. So, what happens to our chemical potential? Edi, it increases because it would take a large amount of energy, okay, to force the gas molecules to interact with each other. Kasi in the first place, guys, dapat very far apart lang yan, okay? So, there is a large increase in the chemical potential. Next, for liquids, there is a moderate increase in chemical potential. So, when you increase the pressure, guys, okay, yung liquid molecules, guys, compared to gas molecules, diba, mas tightly held sila, mas malapit sila to each other, okay? So, nangyayari, pag you increase the pressure, you let them interact more, slightly, with each other more, diba? However, compare mo sa gas, yung difference yan, chemical potential, moderate na lang ang increase, diba? Kasi in the first place, guys, ang liquids nyo, okay, they are much more closer together, okay, compared to the gases, okay? That's why you would need lesser amount of energy in order to drive the liquid molecules to interact with each other, okay? Or to add another particle in the liquid molecule, okay? Again, guys, tingnan nyo si liquid, mas tightly held ang kanyang molecules, right, compared to gases. So, parang mas sanay sila na yung mas sanay ang mga liquid particles to interact with each other compared to the gas particles. Lastly, for solid, edi mas sanay yan, diba? Mas sanay yan. Okay, so here guys, we have a slight increase in chemical potential. We know that in solids, diba? The molecules, they are very packed tightly, diba? So in solids. So, when you increase the pressure further, then syempre guys, yung mga molecules na yan, tightly packed na siya in the first place. Kung i-increase mo yung pressure, then they will just, be pushed together only slightly, diba? Kasi in the first place, very tightly held na sila sa solid mo. So they will only, be pushed against each other very slightly. And that only requires little amount of energy to add more one particle. Guys, sanay na yung solids natin na nag-interact yung mga molecules nila with each other. That's why there's only a slight increase in chemical potential. Now, anong dinidescribe ng slope na ito? So this slope, okay, describes the change in the chemical potential as the pressure changes. So guys, if this increases, di ba? If this increases, meaning the slope also increases. Tama naman, di ba? The slope increases, okay? Kasi positive yung slope natin this time. It is just equal to V, okay? So sinasabi lang dito guys, this tells us how chemical potential will change when pressure changes, okay? And the rate of change of mu with pressure is just equal to the volume of the substance, okay? So sinasabi lang dito guys, when you increase pressure little by little parts, okay? When you increase pressure slightly, the chemical potential, it will increase by an amount proportional to the volume of the substance, okay? So this just summarizes the graph earlier, okay? Let's proceed. So this time, let's determine the chemical potential of liquids, okay? So at equilibrium, the chemical potential of component A, mu A, in the vapor phase, okay, must be equal to the chemical potential of A in the liquid phase. Diba? Let's say guys have two phases, okay? Ang chemical potential ni A in the gas phase and liquid phase must be equal at equilibrium kasi walang nangyayaring net transfer, okay? So sinasabi lang dito guys, there's no net change between the liquid and vapor phase, okay? Anong mangyayari if the chemical potential of in the liquid phase is greater than that of the vapor phase? Guys, ang mangyayari, si component A, gusto niya nang mag-evaporate, okay? A wants to evaporate, it wants to go to the vapor phase, okay? So from, it wants to go to a lower energy state, okay? Kaya, okay, it will want to go to the vapor phase, okay? Next, the chemical potential of liquid, if it is less than the chemical potential of A in the vapor phase, then A wants to condense, okay? It will go to the liquid phase. Again, yung direction ng ating chemical potential is toward lower energy states, okay? Because again, the substance, it always moves from higher chemical potential to lower chemical potential, okay? Hanggang silang dalawa ay maging equal na at equilibrium, okay? So imagine you guys, meron kayong component A, okay? Magko-condense yan or mag-evaporate, okay? Depende sa system mo until they are both equal in the vapor and liquid phase, until their chemical potentials are equal in the vapor and liquid phase, okay? I hope that's clear, guys. Now, here we have the chemical potential of ideal solutions. So guys, we have two types of liquids kasi, ideal solutions and non-ideal solutions. Okay? Pag sinabi natin ideal solutions guys, ideal lahat. So meaning, yung mga intermolecular forces between them, it's not being considered, okay? And particularly guys, we will use the Raoult's law, okay, in determining the chemical potential or the partial vapor pressure or vapor pressure of mole of the A in the mixture, okay? So sinasabi lang ng Raoult's law guys, okay? PA is equal to XA times P naught A. PA is the pressure of component A in the mixture, okay? Or how much vapor ang binibigay ni A, ang ginigive of A. P naught A, P naught A, it is the pressure of pure A. Pure A. If A was just itself, okay, hindi siya nasa solution. And XA, it is the mole fraction of A in the mixture, or how much A is present, okay? Then, this Raoult's law just indicates to us that when you mix something such as A into the solution, okay, nagpo-contribute siya ng less vapor than if it were pure. Kasi nasa solution siya, guys. Nasa solution siya, okay? And the amount it contributes, okay, depends on how much of it is in the mix. So, yun yung binibigay ng inyong mole fraction dito. Okay, again, the amount of vapor na kinocontribute to A depends on how much of A is in the mixture, okay? If you have less amount of A, so let's say low ang mole fraction of A, then that gives less vapor pressure. Diba? Mag-decrease din si vapor pressure for your solution. Okay? So here, for the second equation here, ito, the total vapor pressure of the solution, P solution, it comes from the solvent. Okay? It depends on the mole fraction of the solvent, how much solvent there is, X solvent, and the vapor pressure of the solvent when pure. Okay? Very important guys. Again, yung vapor pressure ng solution mo is dependent on the solvent. Okay? So the more solvent you have, guys, the more solvent you have, so greater ang mole fraction of solvent, then the vapor pressure of the solution will also increase. So it adds to the vapor pressure, okay, ang ating solvent. Lastly, for this one, okay, this just describes again the mole fraction, okay? So we can get the mole fraction of A using PA divided by P naught A, diba? Based on this law. Lastly, guys, we have this equation on chemical potential. So now we can derive the equation for chemical potential from the Raoult's law. So UA is equal to mu naught A plus RT ln XA, okay? And sabi lang ito, guys, the chemical potential of A in the mixture is just equal to the chemical potential of pure A, okay, plus RT ln XA, or how much A is in the mixture. Or in other words, okay, guys, the more you dilute A, so magiging smaller ang XA mo, the more you dilute A, then the lower is its chemical potential. Or the lower is its drive or tendency to change. Kasi dilute na guys, C component A sa mixture mo. So, mag-lower din ang chemical potential, mag-lower yung tendency ng substance to change. Okay? Kasi tandaan guys, chemical potential is like the energy push or the drive of a substance or how badly it wants to escape, react, or move. Okay? Kasi guys, pag dinilute si A, diba, there are fewer A molecules around. And then A will now be surrounded by mostly other stuff, diba? Like the solvent kapag diluted siya. So, si A, okay, it feels less pressure to leave. Okay? Para kang kunwari, nasa big crowd ka. Kasi ikaw yung introverted, quiet person in a big crowd. Ganon si A pag dinilute siya. Okay? So, it has less ability to act or drive change. Therefore, due to its less presence and less energy push it needs, therefore, it has a lower chemical potential. Okay? Ganon yun. I hope that clears out everything, guys, regarding Raoult's law and the chemical potential of ideal solutions. Okay? Again, chemical potential decreases with decreasing XA as well. Okay? Because when you mix A with another component or you dilute it in your solvent, then that increases entropy and makes the system more stable as well. Okay? So here, guys, we have this graph. Okay? And we have, let's say, a mixture of benzene and methylbenzene. Okay? Makinig, guys. Okay, so here, benzene and methylbenzene, okay, each one of them, they will evaporate a little, okay? And when they evaporate a little, okay, that will contribute to the total vapor pressure, okay? So, sinasabi lang ito guys, the more benzene you have, so let's say, benzene has a higher mole fraction. So guys, kung merong higher mole fraction si benzene, then what can we say about the mole fraction of methylbenzene? Oh, then it is lesser, it is lower, diba? So, if this x-axis here is the mole fraction of methylbenzene, then kung mas maliit ang mole fraction ng methylbenzene, dapat sa taas ang kay benzene. Okay? So let's say na somewhere here. Okay? If benzene it has a higher mole fraction, therefore less mole fraction of methylbenzene, then benzene, okay, because it has a higher mole fraction, it will contribute more to the vapor pressure. O tingnan niyo dito guys. Kung sabi natin high ang mole fraction ni benzene, meaning low ang mole fraction ni methylbenzene. So let's say around dito. Look at the vapor pressure. Okay? The vapor pressure of benzene it is much higher, di ba? Around 50 plus compared to methylbenzene, di ba? Nandito lang. So meaning yan, benzene, it will contribute more to the total vapor pressure ng solution mo, ng mixture mo. So benzene will contribute more to the total vapor pressure of your solution compared to methylbenzene because you have a high mole fraction for benzene. Oh, next, what about guys, kung high naman ang mole fraction ni methylbenzene? So let's say ito, di ba? Here we have a higher mole fraction for benzene. Malapit na tayo sa 1, di ba? Okay? Now, compare natin ang vapor pressure ni methylbenzene with respect to methylbenzene and benzene. Oh guys, higher na ang vapor pressure ni methylbenzene, okay, compared to benzene nandito, di ba? Tandaan guys, 0 to 1 meaning guys, here at 1 we have pure methylbenzene. Ito, sa 0 we have 0 amount of methylbenzene. Tapos, kung 0 methylbenzene to, then meaning, meron kang 100% na benzene dito. Okay? Ganon mag-interpret. Okay? So, masasabi natin dito guys, each liquid, they will contribute to the total vapor pressure based on how much of it is in the mixture, di ba? Dependent siya sa mole fraction. Dependent tayo sa amount of the components natin. Okay? So, more benzene meaning more benzene, okay? Vapor. More benzene vapor pressure. Okay? Ayun lang. So, now guys, let's look at the chemical potential of real solutions. So, syempre, kung meron tayong ideal solutions, meron tayong real solutions, di ba? Okay. So, bakit iba yan? Non-ideal solutions guys, okay? Their components, they will differ in structure. Okay? So, what it means, guys, here, we have it based on the Henry's law. So, hindi na natin sinusunod ang Raoult's law. Henry's law na. Okay? So, PB, that represents the vapor pressure of substance B. Okay? Represents how much of B will evaporate into the air, diba? Next, CB, it is the concentration of B in the solution. How much of B is being dissolved in the solution. And then KB, it is your Henry's law proportionality constant. A constant that depends on how easily B will evaporate. Okay? It describes again how easily B evaporates. Okay? So, here guys, nasabi nito, the more B you dissolve, okay? The more B you dissolve, then the more component B will go into the air and evaporate. Okay? Yun yung described ng vapor pressure. Okay? And then guys, recall from our previous crash course, vapor pressure, it determines how much of the component will escape into the air. Okay? And this is reflected by how much is in the liquid, CB, times how easily it escapes, which is a constant, diba? Again, PB, how much vapor pressure, how much of B escapes into the air. Okay? Yun yung describe na. Okay? So, real life example. So, for example, si concentration ng B, okay? For example, it describes how much carbon dioxide will be dissolved in the drink, diba? Let's say, describe natin how much ang concentration ng CO2 dissolved in the drink. So, sinabi natin KB, guys, okay, it's a concept that describes how easily carbon dioxide will escape from the liquid. Okay? And when you say PB, okay, it represents how fizzy or pressurized, okay, it is when you open it. How pressurized yung soda kapag binuksan mo siya. Okay? Yun yung describe ng vapor pressure. I hope that's clear, guys. Okay? So here, correction lang. So, kindly disregard this lang, okay? Ayan. So, let's move on, okay? So, the enthalpy and entropy and gives free energy of mixing, guys, okay? It describes how mixing affects the thermodynamic variables, okay? So, the driving force of mixing, guys, is the increasing entropy of the mixture as molecules interact. So, guys, again, ang basis natin dito is when you, for example, mix the substances in a mixture, okay? Ay di nag-increase din ang entropy, diba? Because the molecules interact with them, with other molecules more, okay? So, we have here the Gibbs energy of mixing. First, the Gibbs energy of mixing, itong equation niya, delta mix G is equal to NTRT times the summation of XI, ln XI. So, when you say XI, guys, that is the mole fraction, okay, of your components, I, okay? This tells us that the energy change, okay, the energy change, when you mix two or more substances, okay? So, two or more substances represented by I, okay? Then, if the value of the delta mix G is negative, okay, mixing happens spontaneously or on its own. Okay? Meanwhile, kung positive yan, you have to drive energy, you have to do work, okay, in order to do the mixing non-spontaneously, okay? Now, mixing, guys, it lowers the system's energy, okay? That's why water and alcohol, they mix easily. Again, this is the equation. Next, we have the entropy of mixing, okay? Here, delta mix S is just equal to negative NT or times summation of XI, ln XI, okay? Again, here, we take into account the substances we have in the mixture, okay? Two or more substances, kaya siya summation, okay? So, it tells us the change in this order when we mix substances. So guys, matic value dapat ng delta mix S nyo ay positive. Kasi this means that mixing increases disorder. Diba? Tama naman, diba? The entropy goes up when you mix. Okay? Because we know that molecules, they get more randomly spread out upon mixing. Okay? And then lastly, we have the enthalpy and volume of mixing. Okay? General delta mix H and delta mix V is equal to 0. Bakit? Kasi for ideal mixtures, guys, okay, the mixing, it should not release nor absorb heat. That's why delta H is equal to 0. Okay? Wala kang net heat. Again, mixing, it will not release or absorb heat for ideal mixtures. Okay? And the total volume will stay the same. That's why delta mix V is equal to 0. Okay? Meaning, walang swelling or shrinking when you add two substances together to form a mixture. Okay? Kaya kayo nag-mix ng colored water, diba? Wala namang tayong heat na give off, diba? And the volume is just the sum of its parts. Okay? That's why delta mix V is equal to 0. Again, this is applicable for ideal mixtures, the thermodynamic properties of mixing. Okay? Now, let's proceed to the next part of our discussion, the colligative properties. So, colligative properties are characteristics of solutions that depend on the amount of a solute and the nature of the solvent, but not on the identity of the solute. Okay? Now, these properties result from the decrease in the chemical potential of the solvent because of the mixing with the solute. Okay? So, sinasabi lang dito guys again, chemical potential, it's like the energy of a substance, right? It is the energy of a substance that has to evaporate, freeze, or escape. Now, anong nangyayari kapag nagdadagdag tayo ng solute sa solvent mo? Okay? So, let's say we have here, okay, a solution. Ito yung solvent mo, nag-add ka ng solute. When you add a solute, guys, okay, the solute particles, pabida yan, it gets in the way of your solvent molecules. So, ano nangyayari sa solute particles mo? Kasi nasa solvent siya. Or ano nangyayari sa solvent molecules mo? Guys, yung solvent molecules mo, they become less free to move kasi meron nang nagdi-disrupt na solute particles sa kanila. Therefore, these solvent molecules have less tendency to escape.
So they will have less energy or less drive to leave the solution. And that means lower chemical potential because they have less energy or drive to leave the solution. Okay? I hope that nagets yan, guys. Okay? So colligative properties such as lower vapor pressure, boiling point elevation, freezing point depression, and osmotic pressure, they all happen because yung chemical potential ng solvent ay nagdi-decrease because you added more solute particles that disrupt the solvent molecules and make the solvent molecules have less tendency to move or less freedom to move. Okay? I hope that's clear, guys. So here again, you have 4 types of colligative properties and we'll go through them one by one. So first we have vapor pressure lowering. Vapor pressure lowering guys, nangyayari yan because you have solute particles hindering the vaporization of the pure solvent. So imagine again, when you have, let's say, a solvent and then you introduce solute particles. Now guys, when you introduce the solute particles, okay, it will hinder the vaporization of your solvent molecules. Again, when you add the solute, syempre your solute will interact with the solvent. So it will hinder the vaporization of the solvent particles. That's why the vapor pressure of the solvent in this solution, when it is combined with the solute, it is lower than the vapor pressure when the solvent is pure. So this is given by this equation here. So we have ideal and non-ideal equations. Okay, so we can use these equations depende kung ang given guys ay for an ideal mixture or non-ideal mixture. Okay, so here we have change in the vapor pressure is equal to the vapor pressure of pure solvent A minus the vapor pressure of solvent A in solution. So kita nyo guys, diba mas mababa ang vapor pressure in solvent A when it is in solution compared to the vapor pressure of solvent A when it is pure, diba? Because of the solute particles hindering it. So this can be expressed in another equation. The change in P is equal to the mole fraction of the solute B, mole fraction of the solute P times the vapor pressure of the pure solvent A. Okay? Pag non-ideal naman, naging AB naman yan. So yung AB guys, yan yung activity ng solute mo. So here, for non-ideal equations, we deal with the activity. Okay? Next, for the osmotic pressures, it refers to the pressure we need to prevent the transport of solvent particles to a more concentrated solution. Okay? To a semi-permeable membrane. So again, ito, pinaprevent natin ang transport ng solvent sa more concentrated solution. Okay? Through a semi-permeable membrane. And this can usually actually be determined through osmometry. You can determine molar mass through osmometry, okay, through this equation. The molar mass, okay, of B is equal to the mass of B, okay, times RT divided by pi V. Okay. So the ideal equation is pi is equal to CRT. Okay. Pi again is your osmotic pressure, C concentration. L and XA is equal to negative pi VA over RT. Okay. Next we have what we call boiling point elevation. When we say boiling point elevation, guys, so imagine you guys, meron kang solvent, meron siyang certain boiling point. Now, kapag nagdagdag ka ng solute particles, okay, hindi nagkaroon ka ng increased interactions between the solute and the solvent. Now, what happens to the boiling point, guys? Nag-increase ang boiling point ng solution mo. It has a higher boiling point, yung pure solution mo, compared to the pure solvent. Kasi, mas nag-increase na yung interactions ng dalawa. So, it would be harder to vaporize the solution, because of the increased interactions between the solute and solvent particles. So, actually, guys, you can also determine the molar mass through ebullioscopy, and this is related to the boiling point elevation using this equation, okay? So, here's the ideal equation. The change in the boiling point, PB, change in boiling point, is equal to KBM, okay? So, guys, usually KB is equal to 0.512 delta degrees Celsius over M. Molal. So M guys, small m, that is molal. So M here guys is your molality. Molal. Again, mole solute over kilogram solvent ang ating molality. Okay? This can also be further solved through this equation, ln XA, okay, which is the mole fraction of A, solvent A, is equal to negative delta VAP H over R times 1 over the boiling point, the normal boiling point, the boiling point of the solvent, minus the boiling point of the pure solvent, minus the boiling point of the solution in general. Okay? We also have corresponding non-ideal equations. The non-ideal equations we take into account I. Okay? So later on we'll discuss I. Then lastly, for freezing point depression, this refers to the lower freezing point of a solution compared to the pure solvent. So guys, when you introduce a solute to the solvent, okay, it lowers the freezing point. Because here naman, you have increased interactions between the solvent and the solute particles. So, okay, the freezing point, okay, becomes lower. Okay? Kailangan mo ng lower temperature in order for freezing to occur. Okay? Mas mahirapan ang ating solution na mag-freeze. Okay? If you have interactions between the solute and the solvent particles. Okay? So actually guys, you can also determine the molar mass determination through cryoscopy. Okay? So guys, possible na basta sa boards, tatanungin sa inyo ang type of molar mass determination method. Ganon. Okay? So the equation is the change in the freezing point, TF is equal to KFM. So KF is usually equal to 1.86. The same units here, okay? I hope it's clear, guys. So to learn more about these colligative properties, kindly watch this video.
Hey, it's Professor Dave. Let's talk about colligative properties.
He knows a lot about the science stuff, Professor Dave explains.
A solution will behave differently from a pure solvent because there are particles of solute that interfere with physical processes like phase changes. A solution will display certain colligative properties that depend only on the concentration of solute and not on the chemical identity of the solute particles. Adding solute to a solvent will change things in the following ways: vapor pressure lowering, boiling point elevation, and freezing point depression. Before we analyze these processes, we need a new way to express solute concentration. When discussing colligative properties, instead of using molarity, we will often use molality, which is moles solute per kilogram of solvent rather than per liter. So the molality of a solution of 10 grams of iodine in 30 grams of dichloromethane would be as follows. We would call this a 1.31 molal solution, like we might say molar when discussing molarity. And while we use an uppercase m to denote molarity, we use a lowercase m in italics to denote molality. When we look at colligative properties, the key theme is that the presence of solute particles interferes with the activity of solvent particles at the interface between two phases. A liquid will always have a particular vapor pressure, since particles at the surface of the liquid can spontaneously enter a gas phase. The number of gaseous particles determines the vapor pressure. But solute particles sitting at the interface occupy some of the surface area, which hinders some solvent molecules from evaporating. Therefore, the presence of the solute causes the vapor pressure of the liquid to decrease. The new vapor pressure is equal to the vapor pressure of the pure solvent times the mole fraction of the solvent, which refers to the percentage of particles in a solution that are solvent molecules. A similar phenomenon is that of boiling point elevation. When a solution is raised to the temperature at which the solvent should boil, again, there are solute particles blocking the solvent molecules from going into the gas phase. This means more heat energy will be needed to compensate for this activity, which results in an elevated boiling point. The more solute there is, the more dramatic the effect. So the change in boiling point is given by the molality of the solution times a constant that is specific to the solvent. Freezing point depression is similar, but deals with the interface between the liquid and solid phases. For a liquid to freeze, it has to form a lattice. The presence of solute particles interferes with the ability of the solvent particles to efficiently form the lattice. So to compensate, the system will have to reach an even lower temperature to freeze. The equation here is similar. The change in freezing point is given by the molality of the solution times another constant. These Kb and Kf constants can be found in tables in your textbook or online. Remember to always add the change in boiling point to the original boiling point, since solute always raises the boiling point, and change in freezing point will always be subtracted from the original freezing point because solute always lowers the freezing point. This is why we add salt to icy streets, because it causes the water to freeze at a lower temperature, so water will remain liquid instead of turning to ice until lower temperatures are reached, thus reducing the quantity of ice that will form. Let's check comprehension. For more
Okay, so yan guys, basically ang ating colligative properties. Okay? Now, what is the Van Hoff factor? So the Van Hoff factor I, so makita natin ito sa mga non-ideal equations natin for freezing point depression, boiling point elevation, etc. Okay? So the Van Hoff factor I shows the ratio of the actual value to the expected value of a colligative property. And this is again needed for our non-ideal equations or non-ideal solutions. And it takes into account the effect of solute on colligative properties by knowing the extent of dissociation of a solute in a solution. Diba guys, in a reaction, okay, solutes, they dissociate in solution when you put them in a solvent. So how do we calculate for the Van Hoff factor I? Using this equation, alpha, which is the degree of dissociation, is equal to I minus 1 divided by V minus 1. So V, guys, represents the number of ions present in your mixture. Okay, I, again, is the ratio of the actual value to the expected value of a colligative property. Again, dapat nilalagay natin sa ating non-ideal equations. Later, you will see that. So here, let's try the sample problem. A 700 gram sample of a compound is dissolved in 750 grams benzene with Kf, okay, freezing point constant equal to 5.12 degrees Celsius over molal. The freezing point of the solution is 1 degree below that of pure benzene. What is the molar mass of the compound? Okay, so here, guys, we have to find the molar mass of the compound. Okay, and we are given the freezing point of the solution. That is 1 degree below that of pure benzene. So, guys, we don't have freezing point values. Ano sabi ko? Reading comprehension na lagi ang kailangan sa mga ganito. Okay, so we know that the change in the freezing point, diba, is just equal to the freezing point of the pure benzene because benzene is your solvent, minus the freezing point of the solution. Gets ba guys? Tandaan, ang freezing point ng solution mo, it is always lower, diba, than the freezing point of the pure benzene. Okay? So, you can use this clue to get the change in freezing point. So, let's solve. The change in the freezing point is equal to the freezing point of the pure benzene, the solvent, minus, sabi dito, the freezing point of the solution is just 1 degree below that of pure benzene. So, that is just simply, if this is the freezing point of the pure benzene, then 1 degree below is just T naught F minus 1, right? 1 degree Celsius. So, distribute na lang to guys, diba? So, magiging T naught F minus T naught F plus 1 degree Celsius. O, syempre guys, mawala T naught F. So, the change in the TF is just equal to 1 degree Celsius, okay? Mag-ingat lagi dyan, guys, okay? 1 degree Celsius. So, we can now solve for the molar mass using the molarity. So, ang key natin dito guys ay ang molarity. Oh, let's try to derive further our equation. So, we know that the change in the freezing point is equal to Kf times mole solute over kilogram solvent. This is your molarity, right? Definition of molarity. Equals to Kf times the mass of the solute over kilogram solvent times molar mass of solute. O, tama guys, diba? Mole solute is equal to mass solute divided by grams per mole. Gets ba guys? Ano nangyayari dyan? Tingnan nyo ng mabuti. Pag ito, ginawa nyo siyang, binultiply nyo siya with mass, diba? You just have to get the reciprocal of this, right? So, magiging mole G, diba? So, makakancel to, si grams, si mass. And ang may iwan ay si mole, diba? So, this is just equivalent to Kf mass solute over kilogram solvent times molar mass of solute. Oh. So, we can now solve, guys, for the molar mass of the compound, diba? Sino naman hinahanap natin? Molar mass ng solute. Kasi yun yung ating solute, yung compound na yan. So, molar mass of the solute of the compound is equal to Kf times mass of solute divided by kilogram solvent times the change in Tf. So, transpose ko lang guys, in-isolate ko lang ang molar mass of solute. And we get 5.12 degrees Celsius over molal. So, this is the given constant times 75 grams solute. Okay, yung mass of solute. Divided by 0.75 kilograms solvent. O, tandaan guys, ang given dito 750 grams benzene. Pero kailangan natin kilograms solvent. So, convert natin ang 750 grams to kilograms. Okay? Again guys ha, 1,000 grams equals to 1 kilogram. Okay? Times the change in Tf, which we know is 1 degree Celsius. I hope that's clear, guys. Okay, tandaan ang dimensional analysis. Okay, tandaan ang dimensional analysis. Solving, we get the molar mass of the solute is equal to 512 grams per mole. Okay, very easy, right? Next, how many kilograms of antifreeze with molar mass 68.3 grams per mole must be added to a radiator containing 7 liters of water if the winter temperature in the area is negative 20 degrees Celsius? What is the boiling point of the water antifreeze solution? So guys, in this case, our solvent is water, antifreeze is our solute. So we are here given actually the freezing point of the solution kasi mahanap natin yung solution ng antifreeze and water within this area with a temperature of negative 20 degrees Celsius. So first guys, let's solve for change in Tf using this equation. We know that the freezing point of pure water is 0 degrees Celsius, right? So that is 0 minus negative 20 degrees Celsius. We get 20 degrees Celsius for our change in freezing point. Solving for the molality using the freezing point depression equation. So the transpose molality, we get change in Tf is over Kf is equal to 20 degrees Celsius, which we solve divided by 1.86 degrees Celsius over molal. Okay? So guys, again, given constant ito, and that is equal to 10.75 mole solute over kilogram solvent. Now guys, using this, we solve for the kilogram of antifreeze needed. So the mass of antifreeze is equal to 10.75 molal, which we solved earlier. So let's convert first. So let's multiply this, okay, to the volume of water. Para makancel natin guys, si kilogram solvent. So convert the ml of water to the grams. So that is based on the density of water. We know that the density of water is 1, right? So 1 gram is equal to 1 ml, so cancel ml. And then convert grams of the solvent to kilograms solvent. Okay? So solving, guys, we get, okay? Actually, guys, dapat, ano to? Ayan. Ayan, tama naman. So cancel, cancel, cancel. Okay? Here, guys. And then, another thing, we have to multiply, okay, this one to the molar mass of the antifreeze packet. Because we have to find the mass of antifreeze. And we can only do that if we cancel the moles here, most antifreeze to the moles of solute. Again, guys, the solute is just your antifreeze. So times 68.3 grams per mole antifreeze. Solving, okay, we get the mass of antifreeze equal to 5.140 grams or 5.14 kilograms. So, nasolve na natin yan, yung kilograms of antifreeze. Next, we solve for the boiling point of the water antifreeze solution. So this is through this equation. So this time, guys, gamitin lang natin ang same molality value natin to get the change in boiling point. Okay? So the change in boiling point is equal to 0.512. Again, guys, this is a constant, 0.512 degrees Celsius over molal. Dapat alam na natin yan, memorize natin yan. Times 10.75 molal. We get 5.51 degrees Celsius. O hindi natatapos yan, guys. Kailangan natin hanapin ng boiling point ng water antifreeze solution. So let's use this. The boiling point is equal to 100 degrees Celsius. So this is the boiling point of the pure water. And this is the change in TB. Diba, guys? Change in TB, okay, is just equal to what? TB minus T naught B. So transpose ko lang si TB, guys, a boiling point ng solution nyo. Okay, so that we can get it. So 100 degrees Celsius plus 5.51 degrees Celsius is equal to 105.5 degrees Celsius. That is the answer. I hope, guys, that's clear. Let's proceed. Ayan, a brine solution containing 1.16 grams of NaCl was dissolved in 50 ml water. What is the boiling point? So, guys, analyze nyo muna anong nangyayari sa sodium chloride nyo when you dissolve it in 50 ml water. It dissociates to Na plus Cl minus. Okay, so, guys, this is a non-ideal solution, diba? Or real solution. So we have to take into account the Van 't Hoff factor I. So how do we do that? Using this Van 't Hoff factor. Okay? Using the degrees of dissociation formula. Degrees of dissociation alpha is equal to I minus 1 over V minus 1. So we know that alpha is equal to 1, diba? For sodium chloride, diba? It completely dissociates in water. So 1 yan. Alam na dapat natin yan. That is equal to I minus 1, which is the unknown, I. 2 minus 1. Bakit 2? Because we have 2 ions present. Again, V represents the number of ions present. So we have here 2 ions present. 2 minus 1. So I is equals to 2. That is your Van 't Hoff factor. Okay? And gagamitin natin yan in future solvings. Okay? So let's solve for the boiling point. So first, guys, let's solve for the moles solute of sodium chloride. Kasi given ng 10 grams. So the moles solute for sodium chloride is 1.96 grams times 1 mole divided by 58.44 grams NaCl. So ginamit natin ang molar mass ni sodium chloride. Solving, we get 0.0216 mole sodium chloride. Okay? Now, ayan, we can now solve for the change in the boiling point. So that is 2. So this is the Van 't Hoff factor we solved earlier times 0.512 degrees Celsius over molal. Then this is a constant times 0.0216 mole sodium chloride, which is the mole solute divided by the kilogram solvent. So convert natin 50 ml solvent to kilograms. So 50 ml water using the density of water, cancel ml, okay, and then you have grams. And then convert grams to kilograms. So we get the kilogram solvent on the denominator. Solving, we get the change in the boiling point is equal to 0.442 degrees Celsius. Now, hindi na tapos yan, guys. We have to solve for the boiling point of the solution. So how do we solve that? Using this equation, okay? So the boiling point of the solution is equal to the change in the TB plus the boiling point of water, your solvent. So that's 0.442 degrees Celsius plus 100 degrees Celsius. Guys, dapat alam yan, okay? Diba? Boiling point of water. And that's equal to 100.44 degrees Celsius. Yan, ang sagot. Okay, guys? Okay. Now we have this another sample problem. The freezing point of a 0.10 molar solution of HF is negative 0.201 degrees Celsius. What is the percent dissociation of HF? Okay? So here, guys, hanapin natin ang I, Van 't Hoff factor, using this equation. Kasi, given na tayo, guys, ng molality, okay, and yung freezing point. Okay? So, hanapin lang natin, guys, i-change in TF. O, diba? Alam natin, guys, that the freezing point of the normal water, okay, is 0, minus the freezing point of the solution, negative 0.201. O, alam na natin i-change in TF, which is 0.201. Let's try to solve. So, the Van 't Hoff factor is equal to, change in TF, which is equal to 0.201 degrees Celsius, divided by KF, so that is your constant for freezing point, 1.86 degrees Celsius over molal, okay, times the molality, times 0.10 molar. Solving, we get 1.08 for I. Okay? So now we can solve for the percent dissociation through this equation. Alpha is equal to 1.08 minus 1 kasi given na ngayon ng I, Van 't Hoff factor, divided by 2 minus 1. Diba? So guys, we have technically 2 ions, diba? Si H plus and F minus ang identities nila. Okay? When it dissociates. So solving, we get 0.08 or 8% ang ating percent dissociation for HF. What does that tell about us? Diba? HF is a very weak acid. That's why it has a low dissociation, low percent dissociation. Okay? Now let's proceed to the activity of ions in solution. So activity of ions determines effective concentration of non-ideal electrolytes. Okay? So the electrolytes, sila yung nasistente ng mga interaction ng mga ions sa solute and the solvent. Okay? So how can we determine the activity of a solute? So that is A. Okay? That is through these equations. Okay? And then, guys, activity, it is proportional to the concentration and the activity coefficient. Specifically for the activity of a non-ideal solution, is described by this. Okay? Naka-blue, guys. Activity is equal to the activity coefficient to the power of the number of species, okay, times, okay, number of cationic species to the power of number of cationic species times, okay, the number of anionic species to the power of number of anionic species, parenthesis, times the molality to the power of the number of total species. Okay? So later on, you'll know how to solve this. Okay? With that, let's try the sample problem. Find the activity expression for the following reactions. Okay? We have sodium chloride here. When it dissociates, forms sodium cation and chloride and ion. Okay? So guys, our species is 2, diba? Because we have 1 sodium cation and 1 chloride and ion. Our cationic species is only 1, which is sodium cation. Our anionic species is only 1 also, which is a chloride and ion. So let's find the activity expression. We have activity is equal to gamma, activity coefficient plus minus squared times 1 times 1 m squared. Okay? So further simplifying this, we get A is equal to gamma plus minus square m squared, diba? Because 1 to the power of 1 times 1 to the power of 1 is 1, right? So matik pala na to. Carry na to. Okay? So this is the activity expression for sodium chloride. Then what about for calcium phosphate? So for calcium phosphate, guys, here we have the dissociation where we have 3 calcium 2 plus cations and 2 phosphate anions. So our number of total species is 5, 3 calcium 2 plus 2 phosphates, okay? And our cationic species is 3 calcium 2 plus, and for anionic species we have 2 for phosphates, okay? So let's find the activity expression. Gamma plus minus 5 to the power of 5 because we have a total of 5 species times 3 to the power of 3. So this is based on calcium 2 plus times 2 to the power of 2, which is based on your phosphates, times molality to the power of 5. Solving, we get A is equal to 108 times gamma plus minus 5 times M to the power of 5, okay? Ganun yun. Next, activity coefficient. Gamma, it accounts for the deviations of solutions from ideal behavior due to the influence of electrostatic attraction. Like, tandaan nyo lang guys ha, pag ideal solutions kasi, okay, ayaw kasi na dapat mag-form ng ions in solutions. Okay? They do not form ions in solutions. Okay? However, non-ideal solutions naman, they form ions called electrolytes. So we have to take into account yung electrolytes na yan. And we can take that into account through the ionic strength. Okay? In order for us to determine the influence of electrostatic interactions between the ions. So here guys, we summarize the various laws and equations on determining the activity coefficient. So this is based on the ionic strength. Okay? Ionic strength. Okay? So we have 3 types. Okay? So first, we have the Debye-Huckel limiting law, used when ionic strength is less than 0.01. Okay? So this occurs for very dilute solutions. So ginagamit natin. So log gamma is equal to A times Z plus times Z minus times square root of I. So later on, we will define the variables. Okay? Again, capital I is for ionic strength. And guys, this tells you how much the activity coefficient drops in very dilute ionic solutions. Okay? And again, it depends on the charge of the ions. So ito yung mga charge ng ions, guys, yung mga Z plus and Z minus. Okay? And then the ionic strength, which describes how many ions there are in the solution. Okay? So, ano meaning nito guys? Yung mga kahit sa very dilute solutions, okay, ions, they still affect each other, okay? And this equation will tell you by how much will they affect each other, okay? Next, the extended Debye-Huckel law, okay? This is used when the ionic strength is between 0.01 to 0.1, okay? And here, we use it for moderately dilute solutions, okay? So it is just like an improved version of the first law. So it includes the ion size A, okay? And it works better for less dilute solutions, okay? So the denominator here, guys, it helps account for how ion size, okay, slows down the effect of increasing ionic strength. Again, slow down niya ang effect ng increasing ionic strength, okay? So, sinasabi nito guys, pag hindi na masyadong dilute yung solution mo, yung ion size, di ba matter na siya? Kasi hindi na siya masyadong dilute di ba? Mas naging concentrated na ng ions ang solution mo. So, this is being described by this equation. Log gamma is equal to A times the charge of the ion and cation times the square root of the ionic strength over 1 plus BA times square root of I. Again, A and B are just constants, so later we will determine them, okay? And lastly, the Davis equation. So, this is very rare to use, but this is used when the ionic strength is greater than 0.1. So, this is used for more concentrated solutions. So, as you can see here guys, di ba? Mas na-improve na siya, okay? Because it works well for more concentrated solution, okay? And it adjusts for stronger ion interactions and reduced shielding effects, okay? I hope it's clear, guys. Now, here are the variables, okay? So again, A is a constant, 0.509. B is also a constant, 0.328. So these are for aqueous solutions at 25 degrees Celsius, okay? And then the charge of the ion is given by Z plus or Z minus. So Z plus, that is the positive charge, Z minus, negative charge, okay? And then A accounts for the ion size parameter for the extended Debye-Huckel law. And then I, dapat important to guys, memorize to, I is equal to 1/2 times the summation of the concentration of the ions times the charge of the ion squared, okay? Ion squared. So yung square na yan, guys, ion lang yan, okay? Ayan. Again, guys, dapat memorize, okay? So first, guys, let's solve the activity of 0.005 molar aqueous solution for the following reaction. Assume DHLL is applicable. So meaning nito, guys, the Debye-Huckel limiting law ang gagamitin natin, okay? So for KCl, let's solve first for the ionic strength. I is equal to 1/2 times the summation of the Ci times Ci, okay? So ito yun, yung dalawang to. First, ang concentration ng potassium plus ay 0.005 molar, di ba? So 0.005 times plus 1, kasi plus 1 ang charge ni potassium, squared, di ba? That's your Z plus. And then plus 0.005, so 0.005, then ang concentration ni chloride na ion, molar, times Zi squared. So that is your -1 squared, di ba? Sinunod tayo, that is equal to 0.005 ang ionic strength mo. This also proves that this is less than 0.01. So the Debye-Huckel limited law ang gagamitin natin in solving for the activity of the 0.005 molar aqueous solution, okay? So the activity coefficient, guys, okay, is gamma is equal to 0.92045, okay? Now let's solve for the activity. So the activity, guys, is given by this expression, right? So solving for the expression, okay, we have A is equal to 0.92045, so that is your gamma, squared, because that is your total number of species, times 1 because you have 1 cationic species and 1 anionic species for me, times 0.005 molar squared. Yun yung ginawa ko. Ayan, guys, so solving, we get 2.12 times 10 to the -5, okay? So lahat yan, pinag-times lang natin, guys, okay? I hope it's clear. Ayan. Ayan, matapos tayo, guys, tapos ko na. Okay, mabilis lang, di ba? So let's recap what we have learned so far. First, it is an intensive property that describes the tendency of a substance to change upon adding 1 mole of a substance to a large amount of mixture at constant T&T. What is that? Yes, that is chemical potential. Next, the ratio of the partial vapor pressure of component A to its vapor pressure as a pure liquid is approximately equal to the mole fraction of A in the mixture. Kanina kaya yun, guys? That is Raoult's law. That's what Raoult's law indicates. Next, the law states that the partial vapor pressure of a solute gas, PV, is proportional to its concentration, with KB accounting for real behavior due to solute-solvent interactions. Yun yan. Henry's law. Lastly, these properties result from the decrease in the chemical potential of the solvent due to mixing with the solute. Colligative properties. Lastly, determines the effective concentration of non-ideal electrolytes activity. Okay? So guys, when we say activity again, it determines the effective concentration of non-ideal electrolytes. Kailangan siya i-take into account. Okay? And yeah, we are done with Crash Course 7. Congratulations, guys. Lapit na tayo. Diba? We are more than halfway through physical chemistry. Okay? So you may now answer practice test 6. Okay? So this is 10 items for 20